You should see the first slide now, and I think this is where we left off. Yep. Start our discussion on enthalpy. Okay. I was trying to move stuff off screen so I can see what I'm doing. Okay. So what is enthalpy? We talked about it a little earlier about the difference between, I think it had to do with path functions versus state functions. And Q is a path function. Q is the actual heat transferred into or out of a system during any process you define. So if it takes you a circuitous route to get to your endpoint, the Q will be different than if you take a direct route. Whereas enthalpy is actually a measure, so to speak, of the potential of a chemical reaction. And delta H, enthalpy, and Q are both, they are equal only when pressure is constant. So when chemists investigate various processes, the tendency is, at least in the beginning, to study the process at constant pressure. That way you get information from Q. The measurement of the heat transfer is Q. You can infer from Q what delta H is under those conditions. Now, if the experiment requires that the pressure changes, then that's a different ball game, and we don't have time to go into it right now, to tell you the truth. Okay, so there it is in black and white. Q is the amount of heat transferred to and from a system. It's one of the two means of energy transfer, right? Heat is one of them. Work is the other. That will change the internal energy of a system. So now our delta E, or change in internal energy, is dependent upon Q and W. We did discuss that, didn't we? Yeah, okay. I just want to make sure it wasn't my imagination. We did talk about internal energy and its dependence on Q and W. So delta H being enthalpy, it's more or less a potential, similar to internal energy. Internal energy and enthalpy are both state functions. But you'll notice from the equation, and yeah, we're going to talk about it. Notice from the equation, maybe I didn't. No, I'm sorry, I got ahead of myself. I introduced the topic without explaining it. So enthalpy is thermodynamic potential and is defined by this equation. The enthalpy change for a system is equal to the change in its internal energy plus any change in this pressure times volume term. And you just have to accept that on faith. That's the way it is, without actually studying thermodynamics in detail. This is one of the products of that study. So when would delta H equal delta E? Well, obviously, when there's no change in this term. If the pressure doesn't change and the volume doesn't change, then delta H is equal to delta E. So internal energy can be measured as long as you keep the pressure and volume constant in a chemical process. But what we want to do is insert an equivalence for delta E, which we know to be Q plus W. So these two terms are Q plus W are delta E. So when we put that in there, we get a slightly different equation, and we're not finished yet, of course. If the process takes place at constant pressure, then we pull this P term out of the expression because it doesn't change. And then the delta says the only thing that changes is the volume right here, whereas P doesn't change. Okay, so now if we substitute the equivalence for a work, which we defined 2 days ago as W equals minus P times delta V, if we substitute that in there for P delta V, then we find that delta H equals Q minus this term plus that term, they cancel out. So that's where we get the definition of delta H equal to Q, only if P is constant. Right, so if P is constant, then the actual heat transfer is equal to the thermodynamic potential called enthalpy. Okay.
Dr. Bly, could you go back to that? I was trying to write all that down.
Oh, okay. Now that's in the slides, right? But the best way to build memories and to ingrain thoughts is to enter data into your brain by as many avenues as possible. So that's why taking notes should still be a part of your lecture experience. I didn't mean to do that. Let's go back. There we go. So if you see something, if you hear it, you write it down. Those are 3 avenues. Now, what other avenues do we have? Well, we have other senses, right? If you try to explain it to somebody, right, speaking, that is a powerful reinforcer for these concepts. If you try to explain it to somebody, or even if you just stand in front of the mirror and try to explain it to your reflection, that's a good way to reinforce this stuff. I remember as an undergrad, one of the things we had to do in one of our courses was prepare a seminar on a topic. It wasn't a very long one, it's like maybe 15 minutes total. But in order to practice, to get everything ingrained, I would go to the animal care room where we kept all our research animals. And we'd have a bunch of rabbits in their cages. And rabbits are very good listeners. So I would stand in front of the rabbits, and that'd be my audience, and I'd deliver my seminar. And I'd just do it over and over again until I could do it without my notes.
I've got it now. Thank you.
Okay. So let's take this example. Let's say you're studying a process that in which the system is at a pressure, volume, and temperature to begin with, and then changes occur in the process. Let's just, for argument's sake, say it's a chemical reaction, and the pressure, volume, and temperature all change in this process. So where does that leave us? Well, the fact of the matter is, between these 2 thermodynamic states, which would be present during the first situation and then change to the second situation, you have many different paths. that you can get there from one to the other. So along each one of these paths, the heat transfers and the work that's done will differ. That's why they're called path functions, because we're actually measuring work performed and heat transferred. And I don't know if it's intuitive, but it should be intuitive that these actual measurements of transfer will not be the same if you take a different path from one state to the next. But no matter which path you take, the heat, the delta H, the enthalpy potential, is the same. It's a state function. It only depends on where you are at the beginning and then where you are at the end, whether it's up here or down here for an exothermic or an endothermic reaction. So I'm trying to draw distinctions here between path and state functions by these examples. That's a typographical error. That should be a capital H. Let's see, where is, okay, here it is. I need to correct that. But the actual enthalpy change that occurs in a chemical reaction can be calculated. If you know the enthalpy of the products, then you subtract the enthalpy of the reactants, you get the enthalpy of the reaction, which is convenient, right? If you know these terms, then you can calculate the potential without actually having to perform the experiment at constant pressure to get the results. That's why state functions are very useful, because it really simplifies the process of getting values. And this is just a reminder, you know, if the P is actually different, then the Q is going to be different than delta H. But if we can guarantee that P1 and P2 are equal, then we can say that Q and delta H are the same. Okay, so we've established that enthalpy is a state function, and only at constant pressure does the Q, heat transfer, equal to the potential enthalpy. Oh, there, I finally got it right. Both capitals. Okay, so let's look at it. That was sort of a thought problem. This is real information, and we're going to extract a calculation, a measurement from this balanced equation. So here we have propane that's being burned, and it gives you carbon dioxide and water. And the equation is balanced for you. You can check it out for yourself, but take my word for it, it's balanced. Now, this delta H, the enthalpy of this reaction, its potential is minus 2,221 kilojoules per mole of propane. Now, that's a lot. That's a lot of energy per mole, right? So if we actually simplify this a little further, it would be 2.2 megajoules. 2,000, let's see, 1,000, yeah, megajoules. So it's a lot of energy. That's why propane is an efficient heating medium or cooking medium, a fuel for your appliances, for your furnace, for your grill. Creates a lot of heat. Now, originally this slide did not have this term here with a slash and mole propane. It's just delta H is minus 2,221 kilojoules. So I stuck the mole propane in here because there's only 1 mole of propane in this balanced equation. But if you don't have this quotient arrangement defined, then many authors I've seen write it like this. Kilojoules per reaction or equation. Now that doesn't mean anything to me. I just assume they just leave it like that. But what does that actually mean? Well, in this particular reaction, it means what I've got on the slide per mole of propane, but it also means for this reaction per 5 moles of oxygen, or per 3 moles of CO2 for that reaction only, or per 4 moles of water. Okay. So depending on what you need in a conversion situation, you can insert the denominator from the equation, and the amount of heat is the same, but your denominator can be different. All right, okay, so that's let's see what the question is. Calculate the delta H in which 5 grams of propane is burned in excess oxygen at constant pressure. Okay, so these are important bits of information. Burned in excess oxygen, that means oxygen is not limiting. All right, so we only have to focus on the propane. And at constant pressure means that when we calculate delta H, we're also calculating Q. All right, so the first thing I want to do, since you can't do any calculations here until you determine the number of moles of propane. So we need the molar mass of propane, and you just calculate it as usual. 3 times 12.01 plus 8 times 1.01 should give you 44.11, or something close to it. And we're going to convert that to how many moles of propane. Turns out it's 0.1134 moles of propane is equal to this 5 grams. So now that we know that, we can use this as a conversion factor to change moles to units of energy. Okay, so that's what we're doing here. We're taking this value and we're canceling the moles of propane, and this numerator gives us the kilojoules, the value of burning 5 grams of propane. You produce 252 kilojoules. Also, I'll call attention to the sign on the delta H. Remember what the sign means. It's all relative to the system. All right, so if we have a system here, then if heat is being added to the system, or anything goes into the system or is done to the system, the value is positive. And if the other way, it's negative. So in terms of heat, this means the reaction is exothermic. If the delta H is negative or the Q is negative, then the process is exothermic. And that makes sense because anybody knows you burn propane, you don't want to stick your hand in it. Unless you want to scorch off some skin. Okay, so that's a calculation. It's a form of stoichiometry in which energy or heat is treated as either a product or a reactant. In this case, if that's negative, which side of the equation would the heat go on if we were to plug it in as a reactant or product? it would be a product. Right? Exothermic means that the reactants yield products, and if it's exothermic, that means there was more energy in the reactants than there was in the products. And now the energy that was over here is a product. Okay? We talked about that a little bit last Tuesday. So if you have a negative value in exothermic, that means the reactants have more energy in them together than the products. And that's a potential energy, of course. Okay. So now we're going to talk about how do you make those measurements. Okay. That's still on screen. Yeah. How do you make those measurements? Well, we use a technique called calorimetry. Calor is I think it's Latin for heat. Anybody that's had anatomy and physiology, or they trained EMT, they'll tell you the things that you look for in infection or injury are 4 things. You look for calor, which is heat. You look for rubor, which is redness, meaning inflammation. Or you look for, let's see, calor, rubor, dolor, which is pain, and the 4th one is tumor, which is swelling, right? So we're interested in the top one, calor, which is heat. So you could feel the wound, or the person, if they've got a disease, they've got an infection, or they're sick in some way, they'll have a fever. You feel for heat. So heat, redness, pain, and swelling are the 4 conditions that define that an EMT would look for, or a doctor would look for. And of course, if you have only 2 of them, or only 3 of them, or something, that gives the professional information about your condition. Okay, so we're going to focus on calorimetry, which is the measure of heat. Metry means to measure, of course. And what we need to do is define some terms first. And actually, these are intensive properties of substances called heat capacity. Now, heat capacity by itself is not an intensive property. It's a capacity factor, because the amount of heat that something has, its capacity changes with the amount of substance that you have. So if you have a lot of substance, it can hold more heat, or it can give up more heat. But that's not particularly useful for doing calorimetry, or for conducting these types of experiments. What we'd like to do is have an intensive property, so that we can, whenever necessary, we can use the specific heat to calculate heat based on how much there is of the substance. So the specific heat capacity is the intensive property of a substance, and it can be expressed in 2 forms. You have your heat units, which will be energy units, joules, right? And it's joules per something. Now, in the first case, specific heat capacity, it's joules per actually joules per degree Celsius per gram of substance. So this intensive property is has two denominator factors. So with every 1 degree change in temperature in 1 gram of substance, you have this much heat change. The other way you can express it is in terms of moles rather than grams. So the other would be, this is just specific heat capacity. This is molar heat capacity. So it'd be the same temperature and the same heat, but instead you have moles in the denominator. And we'll be using both kinds. Now when you're actually doing the experiment, this is the one you'll use, because I don't know of any instrument that's smart enough to measure moles of substance. You got to measure grams and then do a conversion. Okay, so those two terms are useful, and you look at them in terms of, oops, I went too far. Let me back up. Here we go. Okay. You look at them in terms of, lost my train of thought. Well, that's dead air. They say in the broadcast industry, you don't want dead air anywhere. So let's just move on, and if the thought comes back to me, I'll give it to you. So let's use this hypothetical. If you have two reactants, they're both at the same temperature, and you mix them together, and the solution gets warmer, what can we say about that? In qualitative terms, we say the reaction that took place is exothermic, because you can feel that heat is leaving the system. The other way around, if it gets cooler, you have an endothermic reaction. And every hospital, every clinic, most doctors' offices have these bags. They're water-filled bags with a little capsule inside that's breakable. Without breaking the bag, you can break the capsule. And then you mix them up. So you're allowing something in that capsule to be dissolved in water, and when it does one of two things. It either gets warmer or it gets colder. And of course, the substance that's in the little capsule is different depending on which one you want. One of them will get warmer, one of them will get colder. Okay, so that's a qualitative expression of what happens. Now, how do you make the measurements in calorimetry? Well, you need a device called a calorimeter. And these devices, if you buy them from a supply house, they're going to be fancy looking, they're going to be expensive, and they're going to be not as functional as the cheap version. So I've always gone with the cheap version. You just put two styrofoam cups together, and you put a lid on it, and you have a hole through it for your thermometer. And the ones that we would be using in the lab and that you'll see me using in my demonstration, but used to have a stirrer in it. But I took that out. The reason being that my stirrers are not anti-corrosive. In other words, they will react with in the chemistry and could influence the results, but certainly limit the life of the stirrer. So I just took the stirrer out, and now what we do is we use the thermometer to stir. And if you're careful and don't bang it around, you don't have any solid objects in there, which in most cases you don't, then you can use the thermometer to stir the substance. You want it to be uniform throughout in order to get an accurate measurement of the beginning temperature and the ending temperature. Okay, so there's your construction. Now, why do we use styrofoam cups? Well, it goes back to my description earlier, or last Tuesday, of the three types of systems. All right, you can have an with their surroundings. You can have an open system, right? So matter can go both ways, and energy can go both ways. Okay, that's open. Or you can have a closed system in which we don't let matter go, just energy can cross between the two. Now, with our calorimeter, what we're doing is we're isolating the system. From its surroundings. We don't want any transfer to go for our isolated system. So we use styrofoam cups, and we're careful not to add or subtract anything from for the matter during the experiment. So we've isolated the system. Now, why do we want to do that? Well, what happens in Vegas stays in Vegas. Anything that happens in that calorimeter, we want to be able to monitor it. We don't want any influence from the surroundings. We want to say, all right, if there's a change happening, I can make the measurement and infer something about the system that has happened in the process. And that's why we need an isolated system. So as a practical matter, when we have an isolated system, and we're talking about heat, then all the energy in terms of heat in the system is equal to zero. Right? Anything that happens in one side, right? We can't create energy, we can't destroy energy. So everything in our isolated system must be equal to zero. So anything we put out here, all of these terms have to cancel one another out to zero. All right, now I'm going to give you an example, of course. Let's see. All right, so there I'm just reinforcing the terms, and everything has to be equal to zero. So how are we going to use specific heat in this context? Right. Well, first we need an expression here. What's going on in the system? And we have different Q terms, heat terms. And we know that the pressure is not going to change because we conduct all of our experiments at this level in atmospheric pressure. Right? So if it's 1 atmosphere or whatever it is at 2,500 feet where we are, less than 1 atmosphere, it stays there. There's no change because we haven't confined the gas pressure. So we have various Q terms that relate to the different individual processes that we can identify in the calorimeter as the reaction proceeds. So this one we think is happening, and this one we think is happening, all the way out to however many we want, however many terms. We rarely go past 4 for our work, and more often than not will be 3 terms. Sometimes we only have 2. But in order to do that, we need to know what is Q equal to. Well, if we have a substance, for instance, if we have water in our calorimeter, then what's happening here would be this Q1 then would be equal to S is our specific heat capacity, which is joules per degree C gram, right? Those are the units. then if we multiply how much of that stuff we have, the mass of our water, which would be in grams. Notice grams and grams cancel now. Right? So we've got one term canceled out. We have joules per degree centigrade now. So if we have a term out here, what's the change in temperature that occurs during the reaction? This is in degrees C, and that cancels. So now all we have left is joules, heat, or energy. And that's what Q needs to be, right? Okay, so this is an expression for determining the heat change in a substance in our calorimeter. So if we put something else in there, say we put a hot piece of iron, okay? It will undergo some change. It has a different specific heat capacity than water does, so it needs to be at a different value. Then we need to know how much of it there is in mass, and then what's the temperature change. So the temperature change is key, how to calculate that in order for all these terms to cancel to zero. So we always say the delta T is always the final temperature minus the initial temperature. Right? That's not multiplying those two together. That's what delta T is. Final minus initial. So if your water starts out at 20 degrees, say room temperature, and we put hot iron in it, and it goes to 50 degrees, then what's the initial, what's the final? That's the initial, that's the final. So 50 minus 20 is plus 30, right? So delta T for this expression would be plus 30 degrees. Now suppose we put iron in there to get that effect, but the iron was at, I don't know, 90 degrees C. But it went down to 50 degrees. Then it had a 40-degree change, but its change was negative because 50 minus 90 is minus 40. So now I hope you're getting the feel for this, that these terms will have negative and minus values, and they'll all sum to zero. Now, why did I choose 50 here? Why did I choose 50 there? Because if you put the hot iron and water together in the calorimeter, then when they reach equilibrium, they're both the same temperature. Right? And that's when the experiment's over, when equilibrium is reached. Okay, so that's just an example. Those two terms together, calculated this way, will give you zero. All right. So let's go back, or let's sidestep parallel. And see that if we put a 100-gram sample of water at 90 degrees in our calorimeter and a 100-gram sample of water at 10 degrees centigrade, what will be the final temperature? Well, there's sort of an intuition about this. And if you put equal masses together, they both have the same heat capacity. So there should be an equal change. Since they're equal masses, there should be an equal change in temperature. So where does 90 and 1 and 10 meet in the middle? It meets at 50. Because 10 plus 40 is 50, and 90 minus 40 is 50. So that's sort of an intuitive. If all these factors are as they are, then it's easy to calculate that in your head. There we go. But suppose you have 100 grams of water at 90 degrees centigrade, and you add to it 500 grams of water at 10 degrees centigrade. Let's see if we can make we know now that it's not going to be meeting in the middle because there's more water at 10 degrees than there is water at 90 degrees. So the influence on the final temperature is going to be greater for the greater mass. They're equal heat capacities, specific heat capacities, but there's a different mass. So they're not going to meet at 50, but are they going to be higher than 50 or lower than 50? They should be lower than 50, somewhere between 10 and 50, because there's a greater mass here, which means more heat capacity. So what would be the final temperature of the water? Let's see, did I put in a slide for that? No, I just gave you the value, 23. In the interest of time, I'm not going to spend time on calculating that one because we're going to do another one. And, well, I'll just set it up for you. So what you would want to do is calculate a Q value for the 90-degree water and add it to a Q value for the 10-degree water. And here you would have S and S are equal. And then you would have mass. This one would be 9 degrees is 100 grams. And this one would be 500 grams. And then you would have a delta T. And the delta T would be final temperature minus initial. There's your unknown, which we know to be 23 degrees, but minus the initial temperature, which was 90. All right, so there's one term. And over here you have this one times final temperature, right? The same final temperature, that's where they meet at equilibrium, minus 10 degrees. So now all of that, and this is plus these two, all of that has to equal to 0. So you just resolve this equation for the one unknown, and it turns out to be 23. Okay, so let me keep up with my hard copy, so I'm running out of time. Let's see, there. Okay, now the next one takes it to the another step. In this case, in our calorimeter, we have 50 grams of water at 10 degrees, and you put in an iron ball, which weighs 50 grams at 90 degrees. So now what we've done is we've not only changed the temperatures that we started, we're giving them the same mass, but we changed their specific heat capacities. So water has 1, here it is 4.18 joules per degree centigrade gram, and here's iron, 0.45 joules per degree centigrade gram. So you would substitute a different value for S for the iron term as you did for the water term, and just solve for the unknown. And in this case, the unknown will be the final temperature. I call your attention, though, to the heat capacity for water is much, much higher, almost 10 times as much as it is for the iron. Which means that for every degree change in temperature of water, you have more heat required than you do for iron. Or you could say it another way. If you have a certain amount of heat, and it's the same for each one, right, for their change of temperature, then what size temperature is required to give you the same heat Q value for water as for iron. For iron, it takes more temperature change to give you the same Q value. That's what a smaller value of S means that the temperature for equal masses, the temperature has to change much more, almost 10 times as much. So this water could change maybe 10 degrees. You'd have to change the iron temperature 100 degrees to equal the same Q. Right, so if we do the same type of calculation, we end up with 18 degrees as the final temperature. Okay, so let's see. The calorimetry lab gives you a lot more exercise, and I've got an explanation embedded in the method itself to help you understand what the calculations mean. And I try to do that also in the demonstration. So I want to be sure that we get through all of our topics, and then if we have time, we'll come back to sample calculations. So now, what does Hess's law mean? Well, think of your chemical reaction, and suppose you have a chemical reaction that's new. It's a novel reaction. You want to know something about it, about whether it's exothermic or endothermic and how much, before you actually do an experiment with it. Right? Because if you conduct the experiment, the reactants may be extremely expensive, right? And if you conduct the experiment with a limited budget, you want to know something about it. You know, am I going to have to micro scale this reaction so I can afford to do it? That type of thing. Or are there safety hazards? You know, is this an extremely energetic reaction? Is it going to blow up in my face? And you can tell that to a limited extent based upon calculations that give you an idea about its exothermic or endothermic properties. So Hess's law allows you to do that. You have this reaction, and you have various other reactions that you know something about. You know the heats for each of these other reactions. Since enthalpy is a state function, it doesn't matter how you get there. You can combine those other reactions into your target reaction equation and use the heats of the individual reactions that you know to estimate, very closely actually, the heat that's either generated or absorbed in your target reaction. Right? So how do we do that? Well, as you may have guessed, there are rules that go along with it. All right, so I talked about those. So let's say our target reaction is this. Nitrogen gas and oxygen gas give you nitrogen dioxide gas. And the enthalpy for that one is 68 kilojoules. So this is, there's no sign out here, so it's automatically a positive. So this is an endothermic reaction. It absorbs energy to get there. Right, so this is a comparison, right? It's not, we know this value to be true. But suppose we didn't, but we did know that nitrogen gas and oxygen gas in this reaction gives us nitrogen monoxide, and its heat is 180 kilojoules. Plus we know that nitrogen monoxide plus oxygen yields nitrogen dioxide. Right? So what you may notice already is that these reactants here and this one are present in our target reaction. This one is present in our target products. And this one, in this case and in that case, are intermediates. In other words, you don't see those in the reactants or the products. So how do we get these two reactions to combine based on Hess's law? Well, you may have to rearrange them so that your summation equation is equal to the target. And this one is, right? There's two NO2s, there's two oxygens, there's one nitrogen. And if you add these together, you know that if this is on the product side here, but it's on the reactant side here in equal amounts, they cancel. That's why you don't see them down here. They just cancel out. All right? So since we didn't have to change these reactions in any form, they just put them together, then all we have to do now is add these two together. And that gives us 68 kilojoules, which is what we had expected. Right? So this one, delta H, is equal to the delta H's of the component reactions that we spliced together. Okay, and this is just an illustration of why that works. It's because Hess's law takes advantage of the state function of enthalpy, which it doesn't matter what the path is. We could go through a dozen different reactions to get to the end, and the delta H would be the same. Okay.
Hess's law illustrates why enthalpy is a state function. For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in two separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the two steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Okay. These individual reactions that we put together to get the net reaction don't necessarily have to be they don't have to be part of the mechanism for the target reaction. They're theoretical. They could be, but they don't have to be. Hess's law says it doesn't matter how you get there, which means that those individual steps don't have to be true. We just have to treat them properly in the manipulations so that they cancel one another out to give us the net reaction. And these are the rules that are part of that process. If we have to take one of those individual reactions and flip it in order to get the terms on the proper sides, then all we have to do to the delta H for that particular reaction is reverse the sign, right? Because if you go from products to reactants as a positive delta H, then if you go from products back to reactants, then the sign has to change, right? It goes backwards. What about if you have to multiply the equation by a constant in order to give you the right numbers of reactants and products? Well, in that case, all you have to do is multiply the delta H by that factor. Say you had to multiply your equation by 2. Then you just take delta H, that's for the original step, multiply it by 2. And then once you manipulated the individual steps to the point that you can add them together, cancel terms, and end up with your net reaction, Then you take those transformed delta H's, not the originals, but the ones that you changed. Then you can add those together. And that will give you the delta H for the net reaction. Okay, so here's an example. Let's see. Am I going to have time to do this? I'll have to hurry. These are the two individual step reactions, a decomposition of ammonia and combustion of hydrogen in the oxygen atmosphere. So you have these values. This is endothermic reaction. This is exothermic reaction. And what we want to do is combine them in such a way that you have nitrogen gas combining with water to give you oxygen and ammonia. Right? So if we inspect the equations, we know that ammonia's got to be on the other side. It's over here on the reactants side. So it's got to be on the product side over here. So that means we have to flip it and change the sign here to a negative. But we also need 4 of these ammonias, right? So we're going to have to multiply that flipped equation by 4. So we take the negative sign number here, multiply by 4. After we multiply the whole equation by 4. How about the other one, water? Well, let's see. We need waters on the other side, right? So we have to flip that one as well. And we need 6 waters instead of 2, so we got to multiply the whole thing by 3. So this sign changes to positive times 3. And I think on the next page we'll show you details of that. Well, this is a strategy, right? When you're solving these types of problems, it's best to work backwards. So the required equation, or the net equation, determines how you treat the individual steps, just like I did there in several sentences. There we go. Okay, so there are reactions again, and let's see. That has to be multiplied by 4. We've already flipped it, right? That's what we did from the previous slide. Here we go. So there we flipped it, changed the sign, flipped this one, changed its sign. Okay, that's the first thing we did. Now we're going to multiply by constants to give us the number of ammonias and waters that we need. Okay. So there we have that, and we've multiplied those factors that we change signs first, then multiply by our factors, and then we have to add them together and be sure that they produce the desired reaction. Right. So we cancel the hydrogens. Notice one's on one side, one's on the other side. And all we have left is nitrogen and water on the reactant side, ammonia and oxygen on the product side. And then this represents an addition of those two together. Okay, so we were able to calculate what to expect from this reaction, and it's extremely endothermic. So it's going to get very cold in this process. Okay, here's a concept that throws some students for a loop. It's called the enthalpy of formation. Not just the enthalpy of formation, but the standard enthalpy of formation. So the standard enthalpy of formation occurs at standard temperature and pressure, 25 degrees centigrade, and 1 atmosphere pressure. But if you have, well, let's see, that's enough information for now. But what does it mean? The standard enthalpy of formation is assigned to a reaction which produces a compound, right? So if you have a compound over here, like water, and we want to know what that is. So the standard enthalpy of formation, you always start with the product. And the product is 1 mole only, right? That's fixed, can't change it. And under standard conditions, this is going to be a liquid. Right, 1 atmosphere pressure, 25 degrees centigrade. It will be liquid. So how do you get there? You get there by reacting elements. So what elements are required? Hydrogen and oxygen in their standard states. So hydrogen in the standard state is like that as a gas under those conditions, and oxygen as a gas. All right? So now you balance from this side only. So this is a situation where you have to use fractions. There's no way around it. And on one of those previous slides, you may have noticed that ammonia was a fractional equation. So how many oxygens do you need to go from here to here? Well, you only need 1 over there, so we need a half. A half of an oxygen diatomic molecule gives us what we need for that formation. How about this one? That's it. 2 of these, 2 of those, you're done. And the delta H sub F naught is assigned to this, a certain value. All right, did I go too far? Let's see. Oh, I'm on the wrong page. Trying to keep track of myself here. No, it was just a definition on that page. Okay, so we can go ahead. The gases are at 1 atmosphere. If you do have to use a solution, say you have a solution over here, right, which is most likely, it will be 1 molar, like 1 mole per liter. So you still have 1 mole, but in that case, it's dissolved in 1 liter of solution. And pure substances are required over here under these conditions. So for an element, nitrogen will be a gas, potassium will be a solid, 1 atmosphere and 25 degrees centigrade define those states of matter. Okay, so I'm not going to spend, well, this allows you, if you know the standard heat of formation for compounds, then you can calculate the delta H, the enthalpy for a reaction. So for this example, we have this balanced equation. And if you know the standard state of formation of water, of carbon dioxide, and methane, then you can determine the delta H for this reaction. Now, why didn't I include oxygen? Because standard states of elements don't have a formation constant. They're 0. That's why this 0 is right here. Right? So the equation then becomes the delta H for the reaction is equal to the sum of the product delta H's of formation. That's what that big sigma means. It means the sum of various components of the delta H's of formation for products minus the summation of all of the delta H's of formation for the reactants. Okay? So if you know all the delta H's for the compounds, elements don't count, then you can calculate the delta H of the reaction. But what you don't want to forget is if there are coefficients right here, well, oxygen, not oxygen, this coefficient, you would multiply the standard heat of formation for water times 2, right? Because the standard heat of formation is based on 1 mole, right? A 1 out here. So if you have 2 of them, you got to multiply it by 2. And that goes into this calculation. So for each individuals that you have in the products, you'd multiply their standard heat of formation times the coefficient, if there is one. Well, there's always one, but if there's 2, 3, 4, definitely multiply by those. Then add those together. Do the same thing for the reactants, and then subtract the reactants from your product. And you've got a really good, very close value for the delta H for that reaction. So now we have two ways of doing it. Right? We can use Hess's law, or we can use the standard heats of formation for each of the compounds in a reaction. Okay, so I got 3 minutes to go. That means, and this is just everything that I told you is here in print. Right? So when we do this reaction, notice that sodium is 0 and hydrogen is 0 because they're both elements, standard state, 25 degrees centigrade and 1 atmosphere pressure. And the only values that you have are for compounds. Okay, so I don't have a lot of time to stand up on my soapbox, so I'll just let you read the, look at the slides and say, this, since we're on the topic of energy or heat, the authors thought it would be nice to stick something in here about sources of heat in most economies. Fossil fuels, right? I mean, fossil fuels are the linchpin of all modern economies. You can't get away from it. Some are moving toward nuclear, which is wise, I think, in my opinion. But wood has become, it's only valuable for individuals in their fireplaces or their stoves. Hydroelectric, there are limited places, limited amounts of water that can be dammed up and used for hydroelectric. Right? So all the major rivers that could produce hydro have been dammed up and used. And then there are other issues, right? The life of the dam is limited. They always tend to silt in behind the dam, so you have to dredge them out constantly, depending on the sediment load that's carried by the river. And then this is just a chart showing over time how has our dependence on sources of energy changed. Well, back in the middle of the 19th century, it was all wood until we cut down all our forests, and then we had nothing left. In fact, the coal industry was first started with wood, right? They made charcoal. But when it really became, in the industrial age, when it really became, started gaining steam, no pun intended, we needed another source of carbon for producing steel. And we found that in coal. And now we use coal, produce coke. And that's what goes into producing steel rather than wood. So that's why this change occurred about that time, where coal became the dominant form of energy. Then in the 50s and beyond, oil took over. Natural gas and oil. By the way, the United States is a net exporter of natural gas and oil now, even more than OPEC nations. And hydroelectric and nuclear have all been a smaller component of energy that we use in any industrialized countries. Back in the 70s and beyond, nuclear took a real hit because of accidents that occurred. I think we've matured to the point, at least the industry has matured to the point where we're as safe as any fossil fuel, and accidents are almost non-existent. The problem is we haven't gotten over the social stigma of nuclear power. Once we do that, then the sky's the limit, because we have an almost unlimited supply of nuclear fuel. Okay, so let's see. I'm not going to go through this because it's right there in print. Right. And I'll be willing to discuss it with you anytime.